today we're going to answer this question on work, energy, and power. This one is the question 3 from this work, energy, and power consolidation material, which have a total of 9 questions. This question 3 said, diagram below illustrate the roller coaster track. Section A, B, and C are frictionless. So let's have a look here to this roller coaster. They say section A, B, and C are frictionless. Okay, that section is frictionless, but there is friction on section D and E. There is friction in that section. The sled with the total mass of 24.7 kilograms is at rest on the top of the left. And this one is some important data. The mass of this sled is equal to 24.7 kilograms. Alright, you have all displacements, all distances here on the roller coaster. Let's go to the question. Say, how does the total mechanical energy of the sled on the top left position compare to the total mechanical energy of the sled at the end of section D? Write down greater than, less than, or equal to, and explain your answer. And the answer is going to be greater than. But now, why is greater than the mechanical energy at the starting point that at the end of point D? Well, because there is friction and therefore mechanical energy is not conserved. That is the answer. You will get 1 mark for saying greater than, 1 for saying that there is friction, and 1 for saying therefore mechanical energy is not conserved. You can mark yourself as you answer this question. And we're moving on. Question 3.2 says, state the work energy theorem in words. It is in the summary of this material. You can go there and get it. However, the work energy theorem is quite simple. This theorem states that the net work done on an object is equal to the change in kinetic energy. That is in word, and guys, in a symbol is quite simple. Net work is equal to the change in kinetic energy. It's going to be given to you, and therefore you shouldn't make a mistake. You just have to learn how to read that one there. If you say that simple theorem, you will get 2 marks, so you can mark yourself as you answer the question. Now, question 3.3. The speed of the sled at the beginning of the section B is 24.25 meters per second. At the beginning of B, it means the speed there at that point was 24.25 meters per second. At the speed at the sled at the end of section D is 18 meters per second. At this point, the speed is 18 meters per second at that specific point there. So we have 2 data, the beginning of B, all right, and then at the end of D. All right, now use the work energy theorem to calculate the friction force which acted on sled on section D. So now we are speaking about the friction that is in this section here. Okay, now the speed at the beginning of section D is going to be that 24.25, because in section B and C there is not friction, so that speed stay the same there, guys. It's the same speed. Now remember, when we're working with work energy and work and energy, it is recommended to do the drawing as well as the forces, represent the forces. All right, this is the surface and will represent the displacement as well. It will help us with the angle. Now, what forces are acting on that box as it moves in section D? Section D is a horizontal section, so this here is section D. All right, so what forces are acting there? Well, there is a normal force. Let's represent it. Normal force there. You can see the angle is 90 degrees with that displacement. We have the weight or gravitational force on the object, and we have friction. We have frictional force. Okay, so let's go to this page here and solve the question here. What we're going to start with the work energy theorem. Net work is equal to the change in kinetic energy. Now, you should remember that the net work is the addition of the work, is the algebraically addition of the work done by all the forces. Remember, when we did the free body diagram here, we have, or the force diagram, we have three forces acting. So it will be the algebraically addition of all the forces. Let me move it a little bit here. Net work is equal to the addition of work done by normal plus the work done by friction plus the work done by gravitational force. This is algebraically addition, okay? And then we are not working with vectors, so direction doesn't have a point here. If we apply now the definition of work, then we have that the work done by normal force is equal to the product of normal force multiplied by the displacement multiplied by the cosine of the angle between the normal and the displacement. If we go here, this one is 90 degrees. Angle between the force and the displacement. That one is 90 degrees. And if you calculate the cosine of 90 degrees, that will give you 0. Therefore, the normal force does not do work, is 0 joules. If we go to the work done by a gravitational force, we get that this gravitational force multiplied by the displacement multiplied by the cosine of the angle between gravitational force and displacement. If we look here, is also 90 degrees. Alright, therefore the gravitational force also does not do work here, and this one is 0 joule. So the only force that does work is the frictional force. Okay, and what will be the work done by friction? Well, done by frictional force will be equal to frictional force multiplied by the displacement multiplied by the cosine of the angle between friction and displacement. And that angle is going to be all this angle here. That is the angle between the friction and the displacement, which is 180 degrees. Alright, so we're moving back here and we have now cosine of 180 degrees. We have an unknown, which is the frictional force. That is what we are looking for, so we are going to substitute this one in there. Alright, so the net work is actually the work done by friction. Is the only force that does work in here. So we have that the work done by frictional force is equal to the change in kinetic energy. The work done by frictional force is friction multiplied by the displacement multiplied by the cosine of 180 degrees. Change in kinetic energy, remember all changes are final minus initial, so we have that is final kinetic energy minus initial kinetic energy. And when you carry on, you remember kinetic energy is equal to half mass multiplied by speed to the power 2. When you substitute there these formulas, we have that frictional force multiplied by the displacement multiplied by the cosine of 180 degree is equal to half mass multiplied by speed final square minus initial speed, half mass initial speed square, and that is the numbers. We have now enough data to substitute everything here. Everything is taken from the picture. All the substitutions are going to be done, so I'm going to do the substitution. We get that the frictional force is going to be equal to 326,12 Newton. That is the answer here. Now, The direction of the frictional force, that should be 326,12 Newton in the opposite direction or opposite to motion. And that is the final answer. So now, if you answer this one, how will you get mark? Well, you will get 1 mark for writing the work energy theorem. Now, when you write the work energy theorem, this one will give you 1 mark, but it could be any of the following formulas. I recommend you to start from the actual one so you can make sure you get that mark. There will be 1 mark for the substitution of the left hand side. This one will give you 1 mark, and there will be 1 mark for substituting the change in kinetic energy. All this one will give you the 3rd mark. I'm sure you did get those marks. And then the final mark is for the calculation for that final answer. Guys, this question is quite simple. Let's go to question 3.3.2. Another question say, use the law of conservation of energy. Now, before law of conservation of energy, you go to the summary page of this material, you will get that the law of conservation of energy is the one that say the work done by the non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. That is the law we're speaking about here. That is the law of conservation of energy. That is that law that say that energy cannot be created nor destroyed, but that is the law we're speaking about. To calculate the minimum length of section E, now we're going to section E here. How far in section E is going to go now? Require for the sled to come to rest. So important, very, very important. This 10, this high here, we cannot use it. We cannot use these 10 meters because we don't know how far is the sled going to stop. We need to know that the final speed is going to be equal to 0. That one we know because it will stop, but we don't know how high from the ground is going to stop, okay? It has the same frictional force as calculated before, so we're going to use the same frictional force. So let's go to answer that question. New page here. And they say use the law of conservation of energy. So work done by the non-conservative forces is equal to change in kinetic energy plus the change in potential energy. Now, the work done by the non-conservative forces, you remember what is a non-conservative forces, and in this case, we're speaking about friction. Friction is the non-conservative forces here. Gravitational force is a conservative force, so it cannot be included here. In other words, this one is the work done by friction. So this one here is the work done by frictional force. Okay? That is what we have here. And then let's break this formula a little bit more. The work done by friction will be the product of frictional force, which we did calculate already, multiplied by the displacement, multiplied by the cosine of 180 degrees, equal to change in kinetic energy. This one is half mass final speed square minus half mass initial speed square. This one, all this one is the change in kinetic energy. Now we're going to all this one plus the change in potential energy. Remember, potential energy is the product of mass, acceleration due to gravity, multiplied by the height. Okay, so here we have mass, acceleration due to gravity, final height, minus mass, acceleration due to gravity, initial height. We're going to speak about this one right now because it could be tricky. You'll say now, but Mr. G, we don't have the final height because it's not 10. Yes, we are going to work with that one. Don't you stress that. Now, before we do that, let's analyze the following. The final speed will be 0 because the object will be at rest. So this here is going to be equal to 0 because the object will stop. Okay? And what else? The initial height is 0 because there is not height. That initial height is 0. If we go there to section E, this is not height. Height there is equal to 0. And height at the top here, we don't know. It's not 10. But let's analyze this final height there. This, what we have is a section that have an incline. This is what we have. This one is 50 degrees. This one is section D. Alright, and we don't know the height. Alright, so we are going to use that one. So we know that this height where the object is going to stop, this height here, is the opposite side to the 50 degrees. Okay, that is the height. Height is the opposite side to the 50 degree, and the hypotenuse is going to be the displacement. That one is the displacement. So using the tricks here, we can see that sine 50 degree is equal to the opposite side, which is height, divided by the hypotenuse, which in this case is the displacement. So if we rearrange this one, we have that height is equal to the displacement multiplied by the sine of 50 degree. It's a very good practice question, this one, guys. We can substitute this one now in the instead of height. Okay, so let's substitute everything. Frictional force, substitute, but no numbers yet. Displacement cosine of 180 degree is equal to minus half mass initial speed square, because final is 0, plus mass acceleration due to gravity height, but the height is displacement multiplied by sine 50 degree. And now we then can substitute all the numbers we have here. So we are going to substitute a little bit further here in just for the space. Now we can go further and calculate what is able to be calculated here. And we get that the displacement is going to be equal to, I got 7,82 meters. That is the displacement of the block, how far it will go from section D before it stops. Okay, and that one is the answer. So now, how are the marks here? Because it seems a lot of work. This one is quite simple. It's not that bad. It's more intimidating. Remember, I did all the steps. You don't have to do all the steps. You don't have to do all the steps. So there is one mark obvious for the starting point, which is the law of conservation of energy. They gave one mark for this step here when you write the formulas of the change in kinetic and potential energy. Remember, not all the time the mark will be allocated in the same way. Now, if we go to this side, they gave one mark for the substitution of the work done by friction. They gave one mark for the substitution of the change in kinetic energy as well as the change in potential energy. Remember, we did mark here the zeros, so that is important. It's part of the substitution, and the final answer will give 1 mark. So it's 1, 2, 3, 4, 5, and 6 mark for this question, guys. This is all for this specific question 2 of this beautiful material. I hope it helped. I hope it's clear. If it's clear, please subscribe for the channel, thumb up, comments, share, and I'll see you next time. Mr. G here.